Hi everyone, this is Maverick Pod, the chemistry guru. Now in this video, we want to run through a question deducing the number of organic compounds from the strong oxidation of alkenes. So let's take a look at this question. Which compounds on complete oxidation with hot acidified potassium manganate will give two organic compounds? Now when the question is asking for two organic compounds, they have to be different organic compounds. So we're given three options: compound number 1, number 2, and number 3. Now, involving oxidation with hot acidified KMnO4, and if you look at the functional groups present in your compound number 1, number 2, and number 3, they are all alkene functional group. So we know that this is your strong oxidation or your oxidative cleavage. So effectively, what we are doing is we will break the carbon-carbon double bond, and based on the groups that is attached to your alkene carbon, it can be oxidized to three different products. So let us just recap that before we apply this to this question here. Now, there are three possible outcomes. If let's say my alkene carbon is attached to two R groups, this will be oxidized to a ketone. And usually what I like to do is I like to remember this as a K for ketone. One way to deduce why this will become a ketone is fairly simple. If you have a C double bond and there's an opening, what we do is we will cover this up with an oxygen. Since oxidation is adding oxygen, if there's a bond that is open, we will cover this with an oxygen. So if it is an RR group, this guy will be converted to a ketone. Now, if it is an RH, this product will be acid. Usually, I'll remember this as A for acid. How do I figure out why this RH group will be converted to my acid group? It's also fairly simple. If there's a C double bond, which is opening, cover with an oxygen. If there's a CH bond, squeeze an oxygen between your carbon and your hydrogen. This guy will be converted to my acid functional group. Now finally, if it is bonded to hydrogen, then it will be converted to CO2 plus water. The product will be carbon dioxide and water. Again, if you do the same idea, involving a C double bond, if there's an opening, cover with an oxygen. If there's a CH bond, squeeze the oxygen between your carbon and your hydrogen. So we will end up with actually carbonic acid. Carbonic acid actually will look something like this. Let me just draw out the structure here. If we squeeze in the oxygen, then we will end up with a compound which will look something like this. This is my carbonic acid, H2CO3, which will undergo rearrangement reaction to give me CO2 plus water. So you notice the product will be CO2 plus water. So there are a few ways for me to remember the products of strong oxidation. One way we can do is we don't need to memorize the product. We just consider if there's a C double bond, cover with oxygen. If there's a CH bond, squeeze the oxygen between my carbon and your hydrogen. Then we can deduce the product accordingly. Or we can just remember if it is RR group, oxidized to a ketone. If it is a RH, oxidized to acid. If it is a hydrogen, oxidized to carbon dioxide and water. So it's actually not that difficult to figure out, involving strong oxidation of alkene. So let us just run through these options involving compound number 1, number 2, and number 3. What are the number of products that can be formed? Compound number 1, altogether I'll have 7 carbon, straight chain, 7 carbon, and I have a methyl group attached to carbon position 2. Now usually if let's say I need to determine the actual products that are being formed, it is a good idea to expand out the compound, draw out the bonds so that it is easier for me to count the number of carbon, easier for me to consider your groups that is attached to a certain carbon as a substituent. For example, this methyl group that is attached to carbon position 2. So it is easier for me to interpret the compound if you draw out the carbon-carbon bonds. Then what we do is use pen or pencil to cut one line to chop the double bond. Then it becomes easier for us to see that, okay, if you chop your carbon-carbon bond in these two places, I'll have 3 pieces. Carbon number 1 and number 2 will be one piece. Carbon number 3, 4, 5, 6 will be another fragment. Carbon number 7 will be another fragment. So we have 3 different pieces. Then what we want to do is now I have 4 different carbons to consider since I have 2 double bonds. So I break one double bond, I have to consider 2 carbon. Now if I have 2 double bonds, if I break both alkenes, I'll have 4 different carbons to consider. Carbon number 2, number 3, number 6, and number 7. So each of these carbon, we will have to consider what groups this carbon is attached to. Is it an RR group? Is it an RH? Is it a HH? then we decide what it is oxidized to accordingly. So carbon position 2, the yellow carbon, is attached to 2 R groups. So this guy will be converted to ketone. Usually what I like to do is I like to put your letter that represents the functional group that this guy will be converted to. I put a K for ketone. Later I can convert this to your product accordingly. Then carbon number 3, which is my blue carbon, is attached to an R group. Look at carbon 3 and the group that is directly attached to carbon 3. So carbon 3 is attached to carbon 4, which is an R group, attached to a hydrogen. This is an RH group. Scenario 2 is going to be oxidized to my acid group. So put A for acid. Carbon number 6, also look at carbon number 5, which is an R group. And carbon number 6 is attached to a hydrogen. This is attached to an RH. Scenario number 2, oxidized to my acid group. So put an A for acid for carbon number 6. Carbon number 7, my orange carbon is attached to 2 hydrogen. This guy will be oxidized to CO2 plus water. So I put a C to represent that this carbon number 7 is oxidized to CO2 plus water. So once I figure out the functional groups that each of these alkene carbon will be oxidized to, then I transfer this accordingly. Again, you notice if I number the carbon, it is easier for me to keep track. My reactant carbon, where does it go in the product? And it is easier for me to figure out the products, and we will not accidentally draw the wrong number of carbon or we accidentally draw the wrong compound. So highly recommended when we do interpretation, we want to number the carbon so that it is easier for me to keep track and account for all the carbons. Alright, so the first guy will be a ketone. Carbon position 2 is a ketone. Then the blue carbon is going to be oxidized to my acid. My carbon number 6, my green carbon, is also oxidized to my acid group. And carbon number 7 will be converted to CO2 plus water. Now, I will have 2 different organic compounds. I have a ketone and I have a diacid. Carbon dioxide is not counted as an organic compound. Carbon dioxide is counted as an inorganic compound. Alright, so number 1, it will give me 2 organic compounds. So number 1 will be part of the answer. Now, how about number 2? Now, compound number 2, how do I interpret this CH2 bracket 4? It is CH2, 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 CH2. It is a continuous CH2 chain 4 times. So again, I draw out the compound. It is easier for us to interpret. Altogether, I have 7 carbon, straight chain 7 carbon, and double bond is between carbon position 6 and position 7. It is easier for me to number this from left to right. So we're not trying to number the carbon according to the IUPAC system. If you want to number this carbon according to the IUPAC system, then actually alkene carbon should be position 1. But now, we're more interested in accounting for the number of carbon. That's why I just write this consistently from left to right. Carbon number 1 is on the left hand side all the way to carbon number 7 on the right hand side. Alright, so same thing if I have 2 carbons to consider. If I break this double bond, the yellow carbon, carbon position 6, attached to carbon 5, which is an R group, and a hydrogen. So this is scenario number 2. This guy will be oxidized to acid. So I'll put A for acid. Carbon position 7 is blue carbon. It is attached to 2 hydrogen. This guy will be oxidized to CO2 plus water. So this is fairly simple. I'll convert carbon position 6 to my acid, carbon position 7 to CO2 plus water. I'll end up with 1 organic compound. Again, CO2 is not counted as an organic compound. Number 3, what I have is I have a double bond between carbon position 4 and position 5. So if you draw out the structure, it is easier to see that my alkene actually is symmetrical. So if you chop the double bond between carbon position 4 and position 5, each of these carbon will be oxidized to my acid group because this carbon is attached to an R group and a hydrogen. So both of them will be oxidized to my acid group, and it turns out that it is the exact same product, exact same acid. So we will count this as 1 organic compound. So option number 3 will not be part of the answer. Option number 2, of course, will also be not part of the answer since I have only 1 organic compound. So once we have deduced all the products involving the strong oxidation for alkene number 1, number 2, and number 3, then we can take a look at the option. Question 1, which one will give me 2 organic compounds, correct? So number 1, yes, I'll have 2 organic compounds. Number 2, number 3, both of them will not give 2 organic compounds. So answer to this question will be option D. Alright, so that was the discussion involving this question targeting deducing the number of organic compounds for strong oxidation of alkenes. So if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.